We shall start with the beginning then. Today we are going to cover up the lecture number 24 of module 3. And in the previous session we have designed a simply supported rectangular section RC beam, and that too singly reinforced simply supported beam. Now today we are going to continue with a similar kind of design, that is design of simply supported rectangular section beam, and we'll be checking out whether we need to design singly reinforced section or the doubly reinforced section. So let's start with the design. Design a RC beam of rectangular cross section to carry a live load of 25 kN per meter. The clear span of the beam is 5.5 meter and the bearing at each end is 300 mm. Use M20 grade concrete and Fe415 steel. So first let me note down the things which are being given. Design a RC rectangular section cross section beam. So the type of section is to be designed is rectangular cross section. To carry a live load of 25 kN per meter. So the live load value which is being given is 25 kN per meter. The clear span of the beam is 5.5 meter. So let me note down, clear span is equal to 5.5 meter. The bearing at each end is 300 mm, that is end bearing. End bearing is 300 mm. FCK is 20 megapascal, Fy is 415 megapascal. Now in the previous numerical or in the previous design, the span which was given to us was effective span. We were given with effective span. Now it is being given as clear span. Now what is this clear span? So here you all are able to see the beam section in the longitudinal direction. If this is the longitudinal section of the beam, then we can say that the in-to-in distance between the supports, distance between the supports, we can call it as clear span. This is clear span. In-to-in distance between the supports, and this is the support at left end, this is the support at right end. So the distance between the two supports we call it as clear span, and this support is given as, the dimension of this support is being given as 300 mm, that is end bearing. Width of end bearing is 300 mm. So this is 300 mm on either side of the beam. The beam is supported on the bearing of 300 mm on either side. It is simply supported. So the clear span is the in-to-in distance between the supports. Now let's calculate the dimensions of the beam section. In order to calculate the dimensions of the beam section, again we'll be referring to clause number 23.2.1, that is page number 37 of IS 456. In this, we are given with span to effective depth ratio as 20 for simply supported beam. Span to effective depth ratio is Are you all able to hear me? Am I audible?
Yes, ma'am. Yes, ma'am.
Okay. Here, but this is just a guideline, that is span to effective depth ratio is to be taken as 20. But this ratio can be varied from 12 to 20 as it is being, as the live load varies, we can vary this ratio of span to effective depth. As the live load increases, this ratio is being comparatively reduced so that we get a higher value of effective depth. Here the live load in this particular numerical, it is being given as 25 kilonewton per meter. So let's consider the ratio as 18, span to effective depth ratio as 18. If we are getting the span to effective depth ratio as 18, so we'll be getting effective depth value as 305.56. See here in this span, if effective span is given, directly you can use the value of effective span here. Or else if effective span is not given, you can use the value of clear span only. It is not a compulsion that you need to use effective span or you need to use clear span. First preference is given to effective span, but if effective span is not mentioned in the numerical, then you can go ahead with clear span. So this is clear span what we have taken here. Clear span divided by the ratio, that is 18, it is been considered, and the value is 305.56 mm. Now we are going to round off this effective depth to the next higher multiple of 50, that is 350 mm. So effective depth is to be considered as 350 mm. Once we get the value of effective depth, we know that the overall depth value is equal to the effective depth plus effective cover, that is D dash. And for the beams, usually we consider the effective cover value as 50 mm. Effective cover as 50 mm. So we get the overall depth as 400 mm. And now we need to decide the breadth of the beam section. As already told, the breadth of the beam section is to be considered as either 200 mm and multiples of 50 along with 230 mm also, along with 230 mm also. So we need to consider 200, 230, 250, 300, 350 and so on. So here what we have considered is 230 mm. Instead of 250 mm. Instead of 250 mm, you may even consider it as 230 mm or 300 mm according to your convenience. But here in this design we are going to consider it as 250 mm. The next thing, in the previous design example, we did not calculate the effective span since in the data, the span which was given to us was effective span. The span given to us was effective span. But here in this design, we are given with the clear span. Since the clear span is given to us, we need to calculate the effective span. And there are codal provisions to calculate the effective span, that is clause number 22.2, page number 34. Page number 32, 34, clause number 22. Yes. Here we have in clause number 22.2 effective span. Unless otherwise, the effective span of the member shall be as follows. If the effective span is specified in the design itself, it can be taken as it is. But if the effective span is not mentioned or if the clear span is given, then we need to calculate the effective span. How to calculate? It is been given. For a simply supported beam or slab. Here the type of beam which we are designing is simply supported beam. Since it is simply supported beam, we are going to consider this particular clause. The effective span of a member that is not built integrally with its supports shall be taken as clear span plus the effective depth of the slab or beam, clear span plus the effective depth of the slab or beam, or center to center of supports, whichever is less. There are two criteria to be considered here. Those two criteria are center to center distance between the supports and clear span plus effective depth. Here, center to center distance between the supports. Here there is one support of 300 mm width and here there is one more support of 300 mm width. So center to center distance, if I need to consider, it is 300 mm divided by 2 plus 300 mm divided by 2 plus clear span. This will give me the center to center distance between the supports. Here, the same thing is being calculated. Center to center distance between the supports is 5.5 meter, that is clear span. This is clear span and 0.3 by 2 plus 0.3 by 2 on either side, half of the width of the support. It is going to be 5.8 meter. Now one more criteria is clear span plus effective depth. Clear span is 5.5 meter and effective depth what we have considered is 0.35 meter or 350 mm. So the same thing is being considered 0.35 meter. So the value is 5.85 meter. Now there are two values for effective span, 5.8 meter and 5.85 meter. So out of these two, whichever gives you the minimum, out of these two, whichever gives the minimum value, that has to be considered as effective span. Always the minimum among the two values, that is center to center distance between the supports and the clear span plus effective depth. Those two values has to be compared and the minimum value among those two is to be considered for the calculation of effective span. Now, next coming on to load calculations. For this load calculations, now the live load which is being given is 25 kilonewton per meter. So, live load is 25 kilonewton per meter. Let's calculate the self weight. In order to calculate the self weight, we are going to consider the cross sectional dimensions of the beam. And in the cross sectional dimension, this dimension is being considered as B and the depth we need to consider it as overall depth. Breadth into overall depth into unit weight of RCC. Depth into overall depth, breadth into overall depth into unit weight of RCC. Here the breadth to be considered is 250 mm, that is 0.25 meter and overall depth is 0.4 meter. So the same thing is being considered. Why am I considering these two values in terms of meter is live load is in terms of kilonewton per meter. So even we want self weight in terms of kilonewton per meter. So we are going to consider the loads or the distances in case of meter and loads in terms of kilonewton. So the total load W is equal to live load plus self weight. That is 27.5 kilonewton per meter. Now we need to calculate the total factored load. We need to calculate the total factored load W. That is total load multiplied with factor of safety. Total multiplied with factor of safety. So 27.5 into 1.5. This 1.5 is again a partial safety factor to be considered for the load combination of dead load and live load. When the structure or any of the RC beam element is subjected to live load as well as dead load, then for the combination of dead load and live load, we need to consider partial safety factor as 1.5 always. So we are getting the total factored load as 41.25 kilonewton per meter. Now the next thing is the design moment and shear. Now again for the simply supported beam, where will be the moment maximum? What is the critical section for the moment? Can anybody tell me the critical section for the moment? Supriya, what is the critical section for the moment?
Yes, ma'am.
What is the critical section for the moment? Midspan or support? What is the critical section for support? Sorry, for beam.
Support.
Support. Then where is the critical section for shear? Abhishek? Abhishek? Anyone?
Ma'am,
Abhishek,
for moment
Midspan.
at center, ma'am.
moment will have the
Center.
critical
Midspan.
section at midspan. Okay, then for the shear,
Support, ma'am.
support. Yes. For the shear, the critical section is support. For moment, the critical section is midspan. So at the midspan, the maximum moment value is to be calculated as WU L square by 8, where WU is the total factored load and L refers to effective span. Once here you calculate the effective span, in further all calculations you need to consider only the effective span, never the clear span. Remember, once the effective span is being calculated, wherever we have the span, we need to consider the span. There you need to consider the effective span, clear span. So the clear span is 5.5 meter, which has been given, and based on calculated the effective span to be 5.8 meter. So hence for further all the calculations we need to consider the effective span, that is 5.8 meter. So if we calculate, we'll be getting the value of mu as 173.45 kilonewton meter. 173.45 kilonewton meter. So let's consider now shear force. The shear is critical at the support section. So WU divided by 2, that is the maximum shear value for a simply supported beam. So that value will be getting it as 119.63 kilonewton. 119.63 kilonewton. With these design moment and shear, next we need to proceed with the calculation of limiting moment of resistance. We need to calculate the limiting moment of resistance. So in order to calculate limiting moment of resistance, as already discussed, either we can use the equation mu limit given in annexure G, or else we can use the equation which is being derived while deriving the ultimate moment of resistance for the balanced section. That is, mu limit is equal to 0.138 FCK BD square. Mu limit is equal to 0.138 FCK BD square. So FCK is 20, B is 250 mm, D, that is effective depth, is 350 mm. So we'll be getting mu limit value as 84.52 into 10 to the power of 6 Newton millimeter, or it can be converted into Newton millimeter to kilonewton meter, that is 84.525 kilonewton meter. Now Mu limit is 84.52 kilonewton meter and this Mu is 173.45 kilonewton meter. Comparing the values of Mu and Mu limit, we can say that Mu is more than Mu limit. Mu is more than Mu limit. Since Mu value is more than Mu limit, we can say that the beam has to be designed as doubly reinforced rectangular section beam. The beam has to be designed as doubly reinforced rectangular section beam. In the previous design, what we had got? We had got the relation Mu is less than Mu limit. So the beam was designed as singly reinforced rectangular section beam. Now here Mu is more than Mu limit. Hence the beam should be designed as doubly reinforced rectangular section beam. Now as the beam should be designed as doubly reinforced section, all the codal provisions which we have used in the analysis of doubly reinforced rectangular section are useful for the design. Now let me go through the annexure G. Okay. Section with compression reinforcement. Doubly reinforced section means now we need to design both tension reinforcement as well as compression reinforcement. So in order to design both the compression reinforcement as well as tension reinforcement, we need to calculate AST1 as well as AST2. That is, the total AST will be getting it by AST1 and AST2. As we have already discussed in the previous sessions, here the doubly reinforced rectangular section is being divided into two sections. That is, the first one is singly reinforced section and the second one is the steel beam, wherein it has both the tension reinforcement as well as compression reinforcement. So now for what amount we need to design the doubly reinforced section? See here, we have the relation Mu minus Mu limit is equal to FSC ASC into D minus D dash. That means the first section in doubly reinforced beam is going to sustain a moment of Mu limit. It is going to sustain a moment of Mu limit. And we have already the value of Mu, that is design moment. Out of the design moment, the Mu limit value of moment will be carried by the first section, that is singly reinforced section. Remaining value of moment is to be considered by the steel beam, what we call it as second section. The remaining moment is to be considered by the steel beam section. So for that value of moment, we need to design the second section, that is steel beam section, so that we get the doubly reinforced section to be safe for the under reinforced category. As we know that here if xu by d is greater than the limiting value, that means if mu is greater than mu limit, in case of singly reinforced section, then we need to redesign the section. But here we are not going to redesign the section, we are going to make it as doubly reinforced section, so that both the sections, the section 1 and section 2, both will be under reinforced. So we are going to check it as, or we are going to design it as now doubly reinforced rectangular section beam, wherein the first section is going to sustain a moment of Mu limit and the second section is going to sustain a moment of Mu minus Mu limit. So That part or the design of tension reinforcement and the compression reinforcement, we are going to deal it deal with that in the next section or in the next class. Till then, we'll wind up for today. If there are any doubts, you may ask. I'll just show you the slides once again. So if you have any queries, you can ask.